All right, hello everybody. Today this video is going to discuss the graphing of sine cosine functions and the changing of k, which is going to affect the periodic length that I specified in the last video. So we talked about amplitude in the last video. Now we're going to kind of mess around with this k. All right, so you'll notice that in front of each of the thetas, or I could replace those as x's as well, but in front of all those is a number or a coefficient, okay? And so what that's going to do is it's going to affect the periodic length of the function, okay? And then also I'm going to kind of give some examples comparing it to the overall graph so you guys kind of see how this all comes into effect. All right, so let's talk about these basic idea, which is, first of all, we need to find the periodic length, okay? To do that, we need to use this formula right here, which is taking 2 pi divided by k. Essentially what we're doing is we're saying, okay, this guy's multiplying what our basic periodic length is. Now we have to divide by it to find out the new periodic length, okay? So if you want to find the new periodic length, you have to find what this value is, which is 2 pi and whatever k is. K is the number that's in front of, in this case, theta. All right? So, with that said, we are going to break down, or we're going to just follow kind of the formula here and find the periodic length. So I'm going to do the first 2 examples, and then I'm going to kind of give you the answers for 3 and 4, 5, and 6. Now you'll notice that I'm using the sine function, but understand that a couple of these do have the cosine function, but from the last video, you guys know that the only difference between the cosine and the sine is kind of where it starts, okay? So I'm just going to kind of use sine as my main guy. And you guys notice in the formula I could easily put cosine here, and it would just affect kind of where the graph starts. All right, so my first thing I'm going to do is I'm going to find the periodic length. So this is the process of finding that. So I need to take 2 pi, and I'm going to do this all in blue so it doesn't get too confusing. So if I take 2 pi, and in this case divide by 2, and so my new periodic length is pi, and that's the new periodic length. And I'll kind of show how that affects this graph over here. So my periodic length of this particular function is just pi. Okay. Now this looks a little bit more complicated, but understand that I could easily rewrite this as y equals sine theta. I'm going to write it the same way. 1/4 theta. Okay. So sine 1/4 of the angle. So now we're kind of in a predicament because now we have fraction over fraction. But understand, I'm going to rewrite this as, let's see, 2 pi over 1 divided by 1/4. And you understand that all I'm doing, I'm writing it this way so you guys understand why it creates this number. But 2 pi divided by 1/4, which follows the thing here. So that is equal to 2 pi over 1 times 4 over 1. That's just basic properties of fractions, in which if I'm dividing by a fraction, I multiply by the reciprocal. And so my periodic length for this particular function is 8 pi, which, again, we'll see the effects of what that's going to do over here. So now, like we did on the last video, we know that a basic sine and cosine function is broken into 4 parts. It's, well, in the case of the sine function, it starts at the midline, goes up to its highest point, or if it's negative, the lowest point, up back through the midline, highest point, and back down, okay? So it hits its critical points, and then it goes through the midlines, okay? So we break it up into 4 parts. If we wanted to find all the parts, we can. That'd be kind of time-consuming, okay? So what we're going to do is we're going to take pi, and I've kind of made this very easy for you, breaking up the periodic length into 4 equal parts. We multiply by 1/4. So we know that the periodic length is pi, right? So this is pi, and I'm going to multiply by, I'm going to make this a kind of a different color, multiply by 1/4. All right, and so my new, or my first interval here, my first thing, yeah, right there, is going to be pi over 4. Okay, so my guy right here is pi over 4. All right. Now, like I've discussed in class, this is not only the first interval, but also what I go by. So my next one is going to be 2 pi over 4. My next one's going to be 3 pi over 4. And then finally 4 pi over 4. Now, the reason why I do it this way, it's easy for you guys to see kind of the pattern, but notice I can simplify these, and we want to make sure we do that. So 2 pi over 4 can easily be written as pi over 2. So this is pi over 2. And then this guy is also just pi, which exactly is correct because we want our graph to be done with his, we want to do one periodic length in pi, and so that makes it the last one, pi. All right, so now let's graph this thing. My amplitude is 1, and it starts in midline because it's a sine function, so it's going to go up to 1, back to the midline, down to, I'm going to go right through the number here, and back up. All right. Woo, that looked pretty good. Do a lot better from that perspective. All right, so now let's talk about what this implication does on the graph, okay? So say, for example, we have the basic sine function here, and you'll notice that because the periodic length is changed to pi, that means that this particular function needs to do one periodic length in this time segment right here. So you can kind of think like a slinky. I have to kind of compress this thing down so it does one periodic length in pi. So let's take a look at what that's going to look like, and you'll notice that if I can get, I got to put this in parentheses with it. Hold on a second. You'll notice that it has still got the same amplitude, but notice it has to do one periodic length in pi, in 1 pi, or pi radians, okay? So also take a look at where it goes through. At pi over 4, it hits its highest point. If I go back to my graph, pi over 4 hits its highest point. It goes to the midline at pi over 2, hits its lowest point at 3 pi over 4, and back through at pi. And this kind of gives a perspective of what periodic lengths are. Notice how it does one whole periodic length there, then it repeats the same exact image there, so on and so forth. So you'll notice that it kind of compresses like a slinky in a way, all right? Now let's talk about this case where I have 8 pi, all right? So if I want to break up 8 pi into 4 equal parts, I'll take my periodic length, which is 8 pi, and I'm going to multiply him by 1/4 because I want to break him up into 4 equal parts. So times 1/4, and then that is going to equal, in this case, 8 pi over 4, which is, oh wait, did I do that correct? Let's see, 8 pi over 1, 8 pi over 4, which would be 2 pi. Okay, now the reason why I was a little confused because, all right, periodic length. All right, we got to understand that this is the first one. I know it has to end at 8 pi. It needs to finish one whole periodic length in 8 pi. The first one's going to be 2 pi, and then I'm going to go by 2 pi. So the next one's 4 pi. The next one is 6 pi. All right. So same kind of motion applies here. It starts at the midline. It goes up, down, through, and over. Now, this is why I think it's important to kind of look at this graph over here, is because if you look at these two things, they look exactly the same. But in all actuality, you'll notice this periodic length is pi, and this guy is 8 pi. All right, and this is where your homework is kind of at fault here, because you're going to look at these graphs and they're all going to look the same, but they're in actuality they are not. And that's why there's the last page on your packet there. So let's take a look at what this is actually doing in perspective of the long-term picture here. And I'm actually going to just make another one here, and let's call this sine parentheses, in this case, pi or x divided by 4. And you'll notice that I'm not even doing one periodic length. It just looks like almost like a square root function here. But notice how it hits its highest point at 2 pi, and then it starts to come down. I'm not necessarily going to change my graph too much because I don't want to necessarily get it all crazy. But understand that this thing is now stretched out like a slinky in a way. Okay, so you kind of got some practice in that. I'm going to kind of show you the different types of ones here. Let's say, for example, I have 8 pi. So you can understand that if you're finding the periodic lengths, take a moment and try it. I'll explain what the answers are here by the graph. But if I put in 8 here, you'll notice that it does one periodic length in pi over 4, and then the it's very constricted, but you'll notice that it does one whole periodic length in pi over 4, and then each little segment here, your intervals are going to be pi over 16, then it's going to be 2 pi over 16, 3 pi over 16, and then 4 pi over 16. And those are going to obviously have to be simplified. But you'll notice how it compressed down to accommodate the fact that it has to cover one periodic length in pi over 4 radians, or 0.25 radian. Yeah, 0.25 pi. All right, now let's let's include some, I forgot to put 2 in here. All right, example 3 had 2, but notice all that does is it still has the same periodic length, but it just extends it up to 2, down to 2, and that goes off of last video. All right, so let's talk about another one here, -2 sine, let's see, over 2. And you'll notice that one periodic length is 2 pi. It's -2, so it's going to go down to -2. Its lowest point is going to be pi, and it's going to go through the midline at 2 pi. Its next highest point is going to be 3 pi, and then its periodic length is 4 pi. So that is example 4. Example 5 real quick. If we do that one, let's see, 3 cosine, and it's 4 pi, or 4 theta, 4 times the angle there, 4x. You'll notice I'll graph the original cosine function. You'll notice that instead of doing, it's very similar to the 4 pi, it's going to do one periodic length in pi over 2. Notice this is the basic cosine function, all right, which does one periodic length in 2 pi. But you'll notice because we have switched the k, it is now going to do one periodic length in pi over 2. Then its other segments are pi over 8. Pi over 8, it goes to the midline here. Then it goes down here to pi over 4. And then let me think here for just a second. Let's see, it's pi over 8, 2 pi over 8, 3 pi over 8, and then pi over 2 is going to be that. All right. And finally, to not take any much more of your time here, -3, -33, you see what happens there, -3 and cosine x divided by 4. And you'll notice this guy has a very long, stretched out periodic length because its periodic length is going to hit at 2 pi, 4 pi, 6 pi, and 8 pi is going to be the periodic length. And you'll notice that it starts at -3 because the amplitude is -3 and it's a cosine function. All right, so hopefully this helped you out a little bit. We'll kind of cover this more in class, but I recommend to you, there's a program called Desmos. If you go to desmos.com, it'll you can mess around with functions all you want. So for example, if I type in, if I want to get really crazy, let's say for example, I want to make this, let's not get that crazy. If I made it 4, and let's say I wanted to make it 1, let's say 10x. You notice the periodic length changes. Let's say I want to make it 100x. All right, it's going to do a lot of periodic lengths in a short amount of time. So I hope you're catching on to the fact that if it's a whole number in front, it's going to compress, and if it's a fraction out in front, it's going to decompress or kind of stretch out, which is very similar to our functions we'll deal with. For example, when we put a in front, when we put a fraction in front of a parent function, it kind of stretches out. All right, and I could go on, but I know you guys are ready to go. All right, so have a good day, and I will see you guys later.